Okay, so this mini lecture is going to look at friction and what are some of the properties and things that are going to be important when we look at friction. We are going to look at friction in two ways. We're going to use two types of friction. One type of friction is when an object is not moving. So, if I have my eraser resting on a table and I push on it, well, I can push on it I'm pushing on it, but it's not moving. Why isn't it moving? Well, the interaction with the table, the friction, is preventing it from moving. When an object is prevented from moving, we call that static friction. So static friction is preventing the motion of an object. The other type of friction that we're going to talk about is what we call kinetic friction. Kinetic friction is when an object is sliding. So if I slide this eraser down my hand, I just tapped it. I'm no longer interacting with it, so it's moving, and in slow motion it would be ignore my hand. It's moving, and then it slowly comes to a stop. So I push it moves a little bit, and then it comes to a stop. It's sliding along my hand. If we roll a ball down a street, eventually it comes to a stop. If a baseball player slides into first base, eventually she comes to a stop. What's causing her to come to a stop has to be a force. She's changing her motion. That force is kinetic friction. So, kinetic friction occurs when an object is sliding. There are other types of frictional forces, and your book does go through them. We're just not going to emphasize them in problem solving. Rolling friction is different than when an object is rolling down a structure versus sliding. Drag, air resistance, we will talk a little bit about air resistance, but drag through a liquid or a fluid is related to the frictional forces. We're not going to go into those details. So what is friction related to? Well, one of the things that friction is related to is the two surfaces. So friction is a surface-surface interaction. You can imagine that if you had a piece of 200 grit sandpaper, something very, very fine, and a piece of 80 grit sandpaper, something much more coarse, those slide differently along a piece of board. The 80 grit, the real gritty stuff, has a lot of friction. The 120 grit, the real smooth stuff, you can almost rub that on your face. It has very little friction. Why does it have so much difference in friction? The surfaces are different. With the 80 grit sandpaper, we have a lot of interactions that could happen as a block, say a block of wood, goes sliding across that surface. It's interacting with a lot of bumps and crevices. Whereas if that same block goes sliding across 200 grit sandpaper, those interactions are much less. So the surface makes a difference. But it's important to remember that it's not just the surface that the object is sliding on. If I have a piece of carpet that I'm trying to slide across my 80 grit sandpaper, that itself has real gritty surface, compared to a nice smooth block of epoxy sliding across my 80 grit sandpaper, that interaction is going to be different. So the property of the two surfaces and how they interact with each other is important in friction. That property of the surface-surface interaction is called the coefficient of friction. So for every surface-surface interaction, we have a coefficient of friction. And the coefficient of friction goes by the Greek lowercase letter mu, like a French cow. Mu. Okay, maybe that's not so funny. All right, so the coefficient of friction, mu. It is for every individual surface-surface interaction. It's empirical. We had to figure it out by experimentation. Now, what's important is that mu is between 0, and if mu is 0, there is no friction. It's a frictionless environment between the two surfaces. And it's always less than 1. So 1 is absolute maximum. If we're calculating the coefficient of friction for two surfaces, and you get a number greater than 1, you have made a mistake. All right? Keep that in mind. So mu, the coefficient of friction, is always between 0 and 1. Well, what else might friction be dependent on? Oh, let's back up for just a second. How is friction dependent on mu? If 0 is the frictionless surface and 1 is the point of most friction, we keep in mind that if I increase mu, I should increase my frictional force. If I make that surface-surface interaction higher, my coefficient of friction becomes larger, then I get more friction, whether I'm static or kinetic. All right, so if I increase mu, I increase my friction. What else influences friction? Let's imagine that you have a block of wood that you're sliding along a table. You're applying a force in that direction to the right. Friction is, this is fine. You're applying a force in the direction to the right. Friction is resisting that motion. So it's applying a force in the direction of the left. How can I make that frictional force be even greater? Well, what if I push down on the block? What if I add a really heavy mass on this block? Now, one might argue that, well, you've just changed the mass of the block. And I'm going to suggest that, nope, we're not changing the mass of the block. The block hasn't changed. I put a mass on top of it, but the block itself hasn't changed. So when I look at the interaction, the friction, which has changed, I can only look at the interactions on the block. Well, what has changed? Now if I'm pushing down on that block, the table has to do even more of my upward force. I'm squishing the molecules of the table even more. What did we say that force was, those molecule squishing force? Well, that was the normal force. So what I'm doing, by adding a block on top, I'm increasing the normal force that's acting on that block. If I increase the normal force, well, then I increase the frictional force. So in both of these relationships, I have a relationship of proportionality. The frictional force is proportional to the coefficient, and the frictional force is proportional to the normal force. Now I'm going to tell you, the frictional force is the easiest formula to remember. I'll give it to you in your equation sheet for tests, but you won't need it, because the friction formula really defines all of physics. It tells us that friction is related to, and I'm going to use the equal sign, and we're going to be very careful about that in just a minute, the coefficient of friction times the normal force. Friction is fun. Physics, we got it. We can remember that. All right. Now I told you there are two types of friction. Kinetic friction and static friction. Now, if an object is just sitting there stationary and I push on it and it doesn't move, I'm dealing with static friction. If an object's sitting there and I push on it and it does move, I'm dealing with kinetic friction. How are they different? Is the normal force different in either of those two situations? No, it's the same object. So maybe the frictions aren't different in magnitude. Yet I'm pretty sure you've had experiences where you know that they are. Imagine that you're wanting to move a dresser across the room in your living room. And you go to push it, it doesn't move. And you go to push it, it doesn't move. And then you're like, okay, I'm going to move. And you push it really, really hard. And finally you get it to move. And then once it's moving, you don't have to push that hard. It's not as hard to keep it moving once you get it moving. Well, static friction is preventing you from getting it to move. Kinetic friction is the friction you feel as you keep moving it, that resistance. Kinetic friction is certainly less than static friction. If the normal force of that object hasn't changed, what has to change? The coefficient. And indeed it does. The coefficient is actually dependent on the type of friction. There's a different coefficient between your dresser and your carpet for static friction than there is between your carpet and your dresser for kinetic friction. So we want to keep that in mind. Kinetic friction will rely on what we call the coefficient of kinetic friction and will have a subscript K. Static friction will rely on what we call the coefficient of static friction and will have a subscript S. For kinetic friction, our frictional force is always equal to, for the most part, for our purposes, the coefficient of kinetic friction times the normal force. So the fun equation certainly applies in full. It's a little different for static friction, and here's why. Let's go back to our example of pushing on a block of wood on the table. If I have a table, and I have my block of wood, and I apply a force to that block of wood of, let's say, magnitude 2 newtons, and it doesn't move because of friction. Friction, then, if it's not moving, it's not changing its motion. If it's not changing its motion, then the net force must be 0. Now, we're only going to look at the forces in the horizontal dimension because we're on a horizontal table. So we're going to not worry about gravity right now. We're not going to worry about the interaction of the normal force up on the table. We're just going to look at those horizontal forces. So if I'm pushing with a force of 2 newtons and it's not changing its motion, what has to be true about the frictional force? It has to be also equal to 2 newtons. So I push a little harder. I push with a force of 3 newtons, and I still don't get that block to move. Pushing that dresser across the room. Well, the frictional force just reacted to that. It's now 3 newtons. It's as big as it has to be to prevent motion from happening. It can change. Well, that means the coefficient's got to be changing. Something's got to be changing. The frictional force, there's going to come to a point where I am pushing hard enough to just break that frictional force. Well, the frictional force can't change the coefficient. That's just the surface-surface interaction. So how does this work? Static friction can change. It's reactive. It's just as big as it needs to be to prevent motion from happening. If it only needs to be 2 newtons, it's 2 newtons. If it only needs to be 3 newtons, it's 3 newtons. At the point where we are able to break that static friction, we're able to move that block, just making it move, or just preventing it from moving. That is the case of maximum static friction. And I am noticing I did neglect to put my kinetic friction there to identify it. So that's the case of, that's an X, maximum static friction. Maximum static friction is equal to the coefficient times the normal force. So that's only at the point, my fun equation is only at the point where I can break through and get that object to move, opposing that static friction. Or it's at that point where it is the last hold and static friction is winning. So that border right there, those are the same. We can't distinguish between them. They're right at that change point. Now, we want to keep in mind the direction of static friction. We mentioned this when we first, and kinetic, when we first introduced the idea. Frictional forces always, we said, oppose the motion. And in the case of static friction, the intended motion of the object. So if I'm pushing on the object to the right, friction is pushing it to the left. If I'm pushing on the object to the left, the static friction is pushing to the right. If the object is moving to the right, the kinetic friction is to the left. If the object is moving to the left, the kinetic friction is to the right. It is always opposite the motion or the intended motion in the absence of friction. And that's important. We can't say it's positive or negative. We have to know the physics behind the situation. And when we do analysis, when we add all the forces together and we include friction in that addition, we have to know our situation. We have to look at our situation and we have to recognize its direction and put it in appropriately. All right, so that's friction. We're going to look at both kinetic. We're going to use kinetic and static. We're going to have to know when to use kinetic and when to use static. And just as a reminder, we mentioned this, but our kinetic coefficient, remember, is less than our static coefficient. It's easier to keep something moving against friction than it is to get it moving against that friction. So keep that in mind as well. All right, good job.